In this video, I'm going to talk about different types of atoms and then go further and look at the bonding that occurs between atoms. But to start off with, I'm going to distinguish between metals, nonmetals, and metalloids. If you look at this periodic table, it's actually color coordinated for you in order to distinguish between metals, nonmetals, and metalloids. The green elements are your nonmetals. Notice most of them are to the right-hand side of that staircase ladder that you see. The brown elements are your metals, and then the purple ones are your metalloids. And so I'm going to go through and describe characteristics of each type of metal, metalloid, and non-metal. But the first thing that you need to notice is that the majority of elements are actually metals. So let's start with discussing metals. A couple of characteristics of metals include the fact that they have a shiny luster, meaning they're shiny. They conduct heat and electricity. Think about the fact that if you put a metal fork into a socket, you'll get electrocuted, while a plastic one you won't. They conduct heat, so your pots and pans, if you actually touch the metal part of the pot, it is extremely hot, while the insulated part you can touch. They're malleable, which means you can pound them down into thin sheets. That's actually a characteristic that Rutherford took advantage of in his gold foil experiment. He got the gold foil extremely thin, and he was only able to do that because metals are extremely malleable. They're also ductile, meaning you can draw them into wires, so all the wiring we have is metal. And the last characteristic is that they are all solids at room temperature. Now, some have lower melting points than others, but all of those melting points are above room temperature. The other characteristic for you to know is that metals tend to have low ionization energies, and that makes sense because they're to the left-hand side of that ladder. Remember that ionization energy for your group 1 metals is extremely low, meaning that it is easy to lose an electron, and as a result, metals form cations. If you also notice on the periodic table that I provided you, it talks about metallic character. Metallic character is just their ability to act as metals and having those metallic characteristics. So it makes sense that as you move from right to left on the periodic table, the metallic character increases. Also, as you move down the periodic table, down a specific group, the metallic character increases as well. So all of these characteristics we've been talking about, the ability to lose electrons, the ability to conduct heat, all of these characteristics of metals increases as you move to the left on the periodic table and as you move down. As I noted before, metals form cations, and as you can see in this diagram right here, group 1 metals always have a positive 1 charge, group 2 have a positive 2 charge, group 3A, notice aluminum's the only one, but it has a plus 3 charge. If you notice the transition metals, a number of them have more than 1 charge. This is a characteristic of transition metals that we're going to study at the end of this video to understand why exactly they have variable charges. For example, iron can be plus 2 or plus 3, while potassium, for example, is always plus 1. Next, we're going to talk about nonmetals. Nonmetals are the exact opposite of metals. So they are not lustrous, they're not shiny, they're poor conductors of heat and electricity, they have low melting points, and another characteristic is that they are not malleable or ductile, and in fact they're quite brittle. Because their electron affinities are so negative, nonmetals tend to gain electrons when they react with metals, and so as a result they end up becoming anions. I'm now going to talk about metalloids, which are on the periodic table in between metals and nonmetals, but also characteristic-wise, also have nonmetal and nonmetal characteristics. The best example to give you is silicon. Silicon looks like a metal, but it's brittle, and it's a poor conductor of heat and electricity, so it has characteristics of both metals and nonmetals. I'm now briefly going to talk about 2 different groups of metals. This is going to be a very broad overview of them because we're going to study these groups in detail when we talk about chemical reactions. Group 1A, those are called alkali metals. Those are extremely reactive with water and oxygen, and just in general, they're extremely reactive. And the reason why is because they have very low ionization energies, meaning they are very much willing to give up their electron, and so therefore it is extremely easy for them to react. Group 2A are your alkaline earth metals. They are not as reactive as alkali metals, but they are still very reactive. I'm now going to leave metals, nonmetals, and metalloids and get more into the nitty-gritty details about chemical bonding. You'll see how characteristics of metals and nonmetals come in when we're talking about chemical bonding. Before we get started, though, I need to actually define what a chemical bond is. A chemical bond enables two atoms or ions to be strongly attached to each other. Now, there are 3 different chemical bonds that we're going to look at. I'm going to briefly touch on each of them, but then I'm going to go into more detail regarding ionic bonding in this video. An ionic bond results from electrostatic forces that exist between ions of opposite charge. They typically occur between metals and nonmetals, because remember, metals form cations while nonmetals form anions. A covalent bond results from the sharing of electrons between 2 atoms, and those 2 atoms tend to be nonmetals. We're going to look at covalent bonding in the next video. Finally, there's metallic bonding. In metallic bonding, metal atoms are bound to neighboring atoms, and the bonding electrons are free to move through the metal. And so we call this the electron seam model, the fact that you have positively charged metal cations that have electrons moving freely through them. The fact that you have these freely flowing electrons is why metals are good conductors of heat and electricity, because the electrons are free to move. They're not stuck as a result of either an ionic bond in which they're being given away or a covalent bond in which they're being shared. Instead, they're free to move throughout the metal. I'm going to touch briefly on Lewis symbols and the octet rule. A Lewis symbol includes a chemical symbol with a dot for each valence electron. Keep in mind that valence electrons are the electrons that are going to be involved in chemical bonding. Your core electrons are not, and so the Lewis symbol enables us just to focus on valence electrons. So here's an example of a Lewis symbol. This is sulfur. Sulfur has 6 valence electrons, and so those valence electrons are represented with dots. We don't consider the core electrons when we write the Lewis symbol because those will not be involved in a chemical reaction. I included the octet rule in this slide specifically because the Lewis symbol helps you to picture the octet rule. The octet rule states that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. If you notice, the Lewis symbol has 4 different sides, and you can fit 2 electrons on each side, so that's a total of 8 valence electrons. So what the octet rule is telling you is that atoms will either gain, lose, or share electrons in order to get that perfect octet, that 8 valence electrons. And notice that 8 valence electrons, the group that has 8 valence electrons, those are your noble gases. So atoms are attempting to assume the electron configuration of noble gases. I'm now going to talk about ionic bonding. In ionic bonding, an electron, or more than one electron, is donated from a metal to a nonmetal. And so the Lewis structures here in this diagram represent that. So sodium donates 1 electron to chlorine. And if you notice, sodium now has a perfect octet, and so does chlorine. We represent the loss of an electron with a positive charge, and then we put chlorine in brackets and have a negative charge for chlorine. Now, unlike covalent bonding, which you will learn about in the next video, ionic bonding, you don't have 1 single sodium bound to 1 single chlorine. Instead, it creates a crystal structure, as you can see in this picture below. And so you have a sodium ion in purple, and it's going to be surrounded by 6 chlorine ions, and same thing with chlorine. This structure maximizes the interaction that positively charged sodium ions can have with negatively charged chlorine ions. Because ionic compounds have this crystal structure, we don't talk about 1 molecule of NaCl. Instead, we're going to be using the term formula units, because as you can see, there isn't just one molecule of NaCl. You have a whole crystal structure that includes the sodium ions and the chlorine ions. I'm now going to talk about the energetics that are involved in the formation of an ionic bond, and this is going to go back to the last video in which we were talking about ionization energy and electron affinity. We're going back to this Lewis structure, which shows the donation of an electron from sodium to chlorine, and the energy that's required to remove that electron from sodium, the ionization energy, is 496 kilojoules per mole. If you'll remember, most electron affinities are negative, and that is the case for chlorine. In order for it to accept an electron, it's actually going to be releasing 349 kilojoules per mole of energy. So ionization energy, the 496, that is an endothermic process because energy is required, while the electron affinity is exothermic. Now, if we add those two energies together, what you'll find is that this is actually an endothermic process. This would not occur if these were the only two energies that were involved. And so as a result, we have to talk about the fact that the formation of the crystal structure of the positively charged sodium and the negatively charged chlorine, that actually has a stabilizing force that results in the release of energy. So specifically, lattice energy is a measure of how much stabilization the arrangement of oppositely charged ions provide. Now, the lattice energy itself is actually the energy required to completely separate a mole of ionic compound into its gaseous ion. So as you can see here, this is the lattice energy that's involved in breaking sodium chloride into its respective sodium ion and chlorine ion. Now, notice that the reaction that I'm showing here, this is actually the exact opposite of what is occurring in the above reaction. And so the energy that's involved is actually not positive 788 kilojoules per mole. It would be negative 788 kilojoules per mole. And so if I were to add all of the energies up, the negative 349, the 496, and negative 788 kilojoules per mole, I would end up with negative 641 kilojoules per mole, which is a favorable reaction. Now, the energy that's released as a result of the attraction between these ions of opposite charge, that makes up for the endothermic ionization energy and therefore causes the formation of ionic compounds to be exothermic. The formula that you have before you, you haven't actually seen, but it's derived from Coulomb's law, which looks at force. What this is saying is that the potential energy of two charged particles, that equals your constant times the charge of the first particle times the charge of the second particle divided by the distance between them. This is almost identical to Coulomb's law. And so what this is telling us is that the lattice energy is going to increase as the charges of the ions increase. And it also tells us that as the distance between the charged particles decrease, that the lattice energy will also increase. The last topic that I need to talk about is transition metals, and specifically ions of transition metals. If you look at the first example, I show you sodium, I show you the sodium atom, and then I show you the sodium ion. If you notice, in order to form an ion, all that happens is that the valence electrons are removed. So for example, sodium has one valence electron, it's from the 3s subshell, and so that when that one electron is removed, you end up with 1s2, 2s2, 2p6. That is the electron configuration of neon. It gets more tricky though when we're dealing with transition metals. Specifically, if we look at iron, which has the electron configuration of 3d6,4s2, that's its condensed electron configuration, it's not as simple. If I just had 4s2, I would lose 2 valence electrons and then I would be done. But notice I have 3d6 in 4s2. And so the d orbitals create the opportunity to lose more than just one set of electrons. So for example, iron could lose 2 valence electrons to have a +2 charge and have a D6 left over, or it could lose 3 electrons and have 3d5 left over. And so both of those occur. So you have iron that can have a +2 charge, you have some ions with a +2 charge, and you have some ions with a +3 charge. And so the culprit in all of this, the reason why transition metals don't have one set charge all the time,